So I now come to the iterative technique. So skipping the, you know, the basic, you can say the technical things involved in reaching this particular method. Why? Because I do not want to emphasize into much of those details. What I intend to show here is some iterative technique and its implementation over a problem. So I am just skipping that part as to how the theory part as to how we reached this iterative technique. Okay, so I just directly come to the Gauss Jacobi method. This is an iterative method for solving a system of equations of the form Ax equal to b. What I do is that I just split this n cross n matrix A as D minus L minus U. Okay, so D is the diagonal matrix associated with A, and L and U, they are basically negative of the lower triangular and the upper triangular counterparts of A, with their diagonal entries being also equal to 0. What does it mean? It means that, for example, if you have this matrix A, then your D is just the diagonal entry 5, 9, minus 7, the rest being 0. L is the lower triangular part with the negative sign. That means it's 3, minus 1, minus 2, and the rest of the entries including the diagonal be 0 because we have already included diagonal in D. And U be similar. So then A can be written as D minus L minus U, and my system can be written as D minus L minus U, X is equal to B. So what I do is that I take I define iterative scheme xk plus 1 equal to gxk plus c, where gxk is d inverse of L plus u xk plus d inverse of b. Well, this is all based on the fixed point theory that we have skipped, and we are not going to be at loss skipping all this given the motive of this lecture. So I eventually, my focus is on this, like xk plus 1 is equal to t xk plus c, where t is d inverse of L plus u and c is equal to d inverse of b. Note that d, L and u be properly and carefully, determined by you. Okay. So if I write it down in terms of individual components, I get xk plus 1 is txk plus c. If I expand this is dxk plus 1 is equal to L plus u xk plus b. So this is what my d is, this is my L plus u. And if I expand, then I would get that for each I equal to 1 to up to n, this is my iterative technique. Okay. And stopping criteria. Well, stopping criteria means that when do we stop? It's based on error tolerance or the maximum number of iterations. So error tolerance I cannot calculate here exactly because what was sorry, I mean the error tolerance is calculated in terms of absolute error, but absolute error is the absolute difference between the exact solution and the numerical solution. But in my case, exact solution is not known to me. This is precisely what my problem is, that I have to determine the exact solution. So determining the exact solution is what I am doing all this for. So how can I calculate the difference between the approximate solution and the exact solution, provided it is not given to me? So for that, the cross-stopping criteria has been uh, devised in such a way, it has been transformed from that absolute error less than error tolerance to this criterion stated over here, in such a way that what I would ultimately want is that the difference between my latest approximation of x and the difference between the previous approximation of x, which is obviously in terms of components given that x is a vector. So I just find out the difference between the latest approximation and the difference between the previous approximation. I take maximum of all those components. So when the maximum of all those components is less than my error tolerance, then I will stop. Or else, if this does not happen, obviously I'm going to take, as explained earlier, I'm obviously going to take into also account the maximum number of iterations, because suppose I do not reach this as even 1,000 iterations, I cannot go on. I'll have to stop somewhere. Okay. Okay, so implementation over here. So if you have this system, let me choose initial approximation to be 0, 0, 0, and x1 is then given by x11, x21, x31. These are the components of x at the first iteration. So using the formula, the iterative formula, this, I calculate x11 as 1 by a11 b1 minus a12, x20 minus a13, x30. So I substitute the values, I get the new value of x11. Similarly, x21, similarly, x31. So my latest approximation is this. So now I check for the difference between the latest and the previous approximation. That turns out to be 33 by 7, which is still greater than epsilon, which I have chosen to be 0.05 over here. So I move on. I move on to next iteration. So when I move on to next iteration, I find out the first component at the second iteration, x12, which is 0.2425397. The second component of x at the second iteration to be this, and the third component of x at the second iteration. So I take the difference between the latest approximation, the previous approximation, which is still greater than epsilon. And so again I go on. So I go on until I find out my x3, and then I see that the difference between the latest and the previous approximation is still greater than epsilon. So obviously I'm going to go to n equal to 4. In the similar way, we can find out x4, and I see that the difference between the latest approximation and the previous approximation is 0.397783. Now it is less than the error tolerance 0.5, and hence my solution is accepted.